Welcome all. This is the second lecture on strength of materials. So this series is important for GATE 2023. So straight away, let us move to questions. Hope you have enjoyed the first session on SOM, and let me do some more good questions. Now this is the first question. Now the first question is, and this is the data for three questions, 31 to 33. Forget about question number. A two-dimensional state of stress in an isotropic material is given by sigma is equal to the stress system is given by there is a scalar quantity C minus 8, 5, 5, 16, where C is a linearly proportional to the applied loading. The failure stress may be ultimate, may be yield depending on the type of material, and it is given as 350. So what are the principal stresses? So first let us take this stress. So the stress is given by, dear students, the stress is given by C, it is a constant, minus 8, 5, 5, 16. Minus 8, 5, 5, let me check, minus 8, 5, 5 and 16, great. And he is asking what are the principal stresses. Let me take C inside. If I take C inside, the stress matrix is minus 8C, 5C, 5C and 16C. This is the state of the stress. Okay, no problem. Minus 8C, 5C, 5C, right. And you compare this with sigma x, tau xy, this is also tau xy, and this is sigma yy or sigma y. So if I compare sigma x is equal to minus 8C, sigma x, and tau xy is also 5C, tau xy, and sigma y is equal to, compare, sigma x is minus 8C, tau xy is 5C, and sigma y is 16C. Great. Now, actually, if I show you a loaded member, if you see sigma, if C is a positive quantity, imagine, I don't know whether it is positive or negative, I don't know. Imagine C to be positive, then you get sigma as minus. It means it will be sigma x. I don't know, sir, so let me check. Okay, and sigma y is plus, therefore 16C. This is sigma y, this is 16C, and sigma x is minus 8C, and there is tau xy, anti-clockwise and x second. This is anti-clockwise and this is clockwise. Okay, and tau xy is equal to 5C. ये anti-clockwise है, तो ये clockwise, right? See, my dear students, there is no need to put pen on paper. Why? Let me tell you very clearly. The sum of normal stress on any two mutually perpendicular planes is constant. It is invariant of theta. What does it mean? It means sigma x plus sigma y can be written as sigma x dash plus sigma y dash, or it can also be written as sigma 1 plus sigma 2. That means on any plane which is inclined at an angle theta, the sum of normal stress on two perpendicular planes is constant. So it means when you are adding sigma x and sigma y, it should be equal to sigma 1 plus sigma 2 also. If sigma 1, sigma 2 are principal stresses, so add, let me check, I'm checking sense, minus 8C, and sigma y is 16C. So what is sigma x plus sigma y? And this is equal to 8C. So when you are adding, so sigma 1 plus sigma 2 should also be 8C. Let me check. एक बार देखना. You add sigma 1 plus sigma 2. This is coming out to be 16. देखो 8C, correct. And if you add these two, it is 26, I think. एक बार check करते हैं. 26, yes. And if you are adding this, it is minus 26. And if you are adding this, it is coming out to be minus 8C. And you should get, dear students, it should be plus 8C. And if you just observe, this is the only option which is giving me plus 8C. So this is the right answer. But now, how to do? If two more values are, say two values are equal to 8C, then what to do? Very simple. Where is the problem? Where is the problem, dear students? Where is the problem? Let me do this. Let me do this. So, एक second. Let me do this. Very simple. So let me erase all. Okay. Now. So we have sigma x is equal to, let me check, sigma x is minus 8C, sigma y is equal to, where is that? sigma y is equal to 16c and tau xy is equal to, let me check, 5c. No problem at all. So if you want sigma 1, it will be sigma x plus sigma y by 2 plus under root of sigma x minus sigma y by 2 whole square plus tau xy square. If you just substitute, you get sigma 1. Similarly, if you want sigma 2, you put it minus. Sigma x, sigma y are known and tau xy is known. If you substitute, you'll get the same answer. So, but anyway, just observing options, I can give the only suitable option is he is just checking whether you know this concept or not. Some of the normal stress on any two mutual perpendicular planes is constant. So he's just checking. When you're adding these two, I should get 8. If you add 16 minus 8, add karo 8c. So this is not giving 8. This is not giving. This is giving minus 8. Agar two options had it been same 8c, then I would have gone for this. I would have gone for this. So if you calculate, similarly, if you want sigma 2, it is sigma x plus sigma y by 2 minus under root sigma x minus sigma y by 2 whole square plus tau xy square. So if you are calculating, I think we get sigma 1 as, where is that? Sigma 1 as 17c and sigma 2 as minus 9c. So this is 17c and this is minus 9c. You just calculate, you put these values. And now, this is the first question. Or next, the maximum shear stress. Very simple. The maximum shear stress is given by sigma 1 minus sigma 2 by 2. So therefore, the maximum shear stress is given by sigma 1 is 17c and sigma 2 is minus, what was the value? Sigma 2 is minus 9c by 2. So therefore, the maximum shear stress is given by, this is 26 by 2. 26c by 2 and this turns out to be 13c. Where is that? Yes, it is 13c. Now the last question in this part. Where is that? The maximum value of c for safe loading of the structure based on von Mises criterion. ये बहुत important है sir. This is very important. The maximum value of c based on von Mises criterion. You know that according to von Mises criterion, and there is no factor of safety given here. So therefore, what I do is, my governing equation as per von Mises is sigma 1 square plus sigma 2 square minus sigma 1 sigma 2 is equal to sigma yield or ultimate, that is failure square. It can be yield or ultimate depending on the material, so square. This is my governing equation as per von Mises. So sigma 1, already you know. What is sigma 1? It is 17c. Let me check. Sigma 1 is 17c and sigma 2 is minus 9c. So sigma 1 is 17c whole square minus 9c. These are principal stresses. Minus 17c minus sigma 1 17c square. Sigma 2 minus 9c square minus sigma 1 17c. Sigma 2 is minus 9c is equal to failure stress is given. Failure stress is given. What is the failure stress given? It is 350 megapascal and that is given as 350 megapascal whole square. And all these are in megapascal, no problem at all. And if you calculate, I think you are getting the value as 15.3. Yes, this is the right answer. This is a very good question, though not tough, but this variety can be expected. So only I'm trying to give you varieties of questions. Chalo. Now let's go to the next question without wasting any time. Okay, we'll take a good question. Take this question. A rectangular thin plate with Young's modulus 200. E is given as 200 gigapascal. So I will write gigapascal as 10 power 3 megapascal. Gigapascal can be written as. Okay. And the Poisson's ratio is given. What is the Poisson's ratio? 0.3. Very good. Now, is subjected to a uniform stress distribution at its edges as shown. However, it is stated that the dimension B, look at carefully, the y-axis is, on y-axis it is B, on x-axis it is A. So this is in x direction, A dimension is in x direction and B is in y direction. What did he say? It is stated, this is very important part, it is stated that B of the plate does not change. What does it mean? So though it is loaded biaxial stress, but the dimension B is not changing. What does it mean? The strain in the y direction is 0. So because the y dimension, in y direction the dimension is B, he said the dimension B of the plate does not change. So therefore, can I write the strain in y direction is 0 because the value of B is not changing? Yes, sirs, no problem at all. And the stress components are given. Okay, considering micro strain, matlab 10.6, the change in length in A, he is asking what is the change in length A? Means he is asking. So let us find out epsilon x, that is strain in x direction. Then we'll find out the change in dimension in A. So you have already studied in our regular classes. Dekho, the strain in y direction can be written as sigma y by E minus nu sigma x by E. But in this problem, the strain in y direction is given as 0. So therefore, this is equal to 0. Take E to this side, so you are left with sigma y minus nu sigma x is equal to 0. Or sigma y is equal to nu sigma x. Wonderful. So can I calculate sigma y? Yes, sirs. It is nu. What is Poisson's ratio? It is 0.3 into sigma x. Already sigma x is given as 200 megapascal. So 0.3 into 200 is 60 megapascal. So my dear students, now let me write on a new slide the state of the stress system. That is sigma x is 200 and sigma y is calculated and it is 60. So let me write sigma x is, take a second, sigma x is given as 200 and we have calculated sigma y just now, and that sigma y we have calculated and its value is 60. Very good, sirs. Now what is he asking? Change in dimension in x direction. So strain in x direction is equal to change in the dimension in x direction. In x direction the dimension is this and the original dimension. Or you know, my dear students, एक second देखना. Yes, okay, no problem at all, no problem at all, no problem at all. It is change in, one second please. This, okay. Let us find out this value. So epsilon x is equal to sigma x by E minus nu sigma y by E. No problem. So epsilon x is equal to sigma x. What is sigma x? It is 200. And denominator is constant, so therefore LCM is same. So Poisson's ratio, I think it is 0.3 and sigma y is 60 divided by E. What is E? What is E? It is 200 into 10 power 3. It is 200 into 10 power 3. This is megapascal, this is megapascal. So let me calculate. 0.3 into 60. This is 182 by, I'm getting this value as epsilon x as 9.1 into 10 raised to minus 4. Let me check once, my dear students. 200 minus 18, correct now? By 200 by 1 exponent 3, that is 9.1. Yes. But what is the meaning of this? Strain in x direction is change in x dimension to the original dimension. In x direction, the dimension is A. So here, this length is given as A. So he is asking change in this dimension, and this is given as A. And what is A given? It is 200. It is given as 200. The original length is 200 mm, and strain is dimensionless. So this is 9.1 into 10 raised to minus 4. So you will get this change in dimension x direction in mm. So this is into 200, and I am getting this as 0.182 mm. This value is 0.182 mm. Let me check, and he is asking in mm, so it is 0.182 is the right answer. Though it is not a tough question, but it is expected question. Okay, chalo. Let's move to the next part. Let's move to the next part. Is mild steel specimen under uniaxial tensile load. This is the member, and this is uniaxial loading. Uniaxial loading, and the Young's modulus is 2 into 10 power 5 megapascal, and the yield is given as 250 megapascal. Okay, the maximum amount of strain energy per unit volume that can be stored in this specimen is, my dear students, when I was teaching you on plus in our regular SOM course, I gave you one equation. The strain energy under uniaxial loading is given by P square L by 2AE. I have derived this equation. I repeat, I have derived this equation. So, but he is asking per unit volume. Let me rearrange this equation. So what I do is P square L by 2AE, and I'll multiply and divide with A. Let me repeat this. I will multiply and divide with A. I'll multiply and divide with A. So the strain energy is given by, बहुत carefully देखना, A into A is A square. So P square by 2E, I repeat, 2E, A into A is A square, and area into length, this is volume. Let me repeat, P square, AL is volume, 2, A into A is A square. Okay, now strain energy per unit volume, you bring volume to this side. What is P by A? This P by area, this area, it is stress. So P by A is stress, but it is P square by A square is sigma square by 2E. And he is asking strain energy per unit volume. Sigma is given, maximum, dekho, the maximum amount of strain energy that can be stored. Okay, no problem. So sigma is given, and already maximum means up to yield. Okay, no problem. And then we have, look at carefully, E is also given. I can easily calculate, but you should be careful with units. Simply you substitute and get the answer. How do, the units are very important. Let me check. He is asking, look at Newton mm per meter cube. So if you observe carefully, sigma is given in megapascal, means Newton per mm square, megapascal. E is also given, but this is whole square means it will be mm power 4. Sigma square is Newton square by mm 4, and E is Newton per mm square. Don't keep it in gigapascal, megapascal. Newton is gone. This is mm square. So you will get the answer as Newton per mm square. It is same as multiply with mm, divide with mm. So whatever you are getting, mm per mm cube is Newton per mm square. So you keep this in Newton per mm square, this in Newton per mm square, megapascal, you will get the answer. Is it clear? I think it is 0.15 something. You just calculate. It is very simple. Next. Let me check. This is a good question. Please read the question. Please underline this term spherical pressure vessel has a mean radius of, and here the radius is given. What is the radius, sirs? It is 1000 mm. So I can write the diameter as 2000 mm. The radius is 1000 mm. As the radius is 1000 mm, diameter is 2000 mm. And the wall thickness is 10 mm. And the Young's modulus is given as 200. Let me write giga. So I write this as 10 power 3 megapascal. No problem at all. And the Poisson's ratio is 0.25. Okay. If the internal pressure is 100 megapascal, let me repeat. The internal pressure is 100. The radial displacement in mm. Okay, no problem at all. We have studied in our strength of materials class. What is that we have studied? We have studied that when a thin spherical vessel is subjected, as it is symmetric, therefore the stresses, that is sigma 1 and sigma 2, both are same. Unlike your cylindrical pressure vessel. In cylindrical pressure vessel, the longitudinal stress and the circumferential stresses are different. But in spherical vessels, due to symmetry, my sigma 1 is equal to sigma 2 is equal to PD by 40. I think you remember this. Is this correct? Yes, PD by 40. No problem at all. Now, how do I calculate? So circumferential strain or radial strain is given by, all are in radial direction only. So this can be written as sigma 1 by E minus nu sigma 2 by E. Very good, sirs. The diametral strain or radial strain is given by this. So this is radial, this is also radial, so no problem at all because it is symmetric. So now, can I write this radial strain as, so sigma 1 by E, because sigma 2 is also sigma 1. Sigma 2 is also sigma 1. So sigma 1 by E, sigma 1 by E, I will take common. This is also sigma 1. 1 minus nu, 1 minus nu. So therefore, now radial strain is given by, he is asking what? Radial strain is given by sigma 1 by E into 1 minus nu. Let me check, sir. Sigma 1 by E, 1 minus nu. Okay, no problem at all. No problem at all. Now, yeah. Where is that? Yeah, this is the one. Now, is the Poisson's ratio given 0.25? Now, देखो sirs, आराम से कोई tension नहीं. But I will write this as sigma 1. Already sigma 1 is PD by 4T into 1 minus nu. What is he asking? Radial displacement. Means he is asking change in the radius. How much radius is displaced? That is, radial displacement is nothing but change in the radius. So radial strain is given by change in radius to the original radius is equal to, check the unit. Keep D and T in same unit, so dimensionless, because strain is dimensionless. These two same unit, and pressure and Young's modulus same unit. Megapascal, megapascal, mm, gone. Now, P क्या है? 100 megapascal. It is 100 megapascal. D, what is D? 2000 mm. 2000 mm by 4. And the thickness, what is the thickness? 10 mm. So 10 mm. And the Young's modulus, where is that? Young's modulus is 200 into 10 power 3. 200 into 10 power 3 into 1 minus nu. And the Poisson's ratio is 0.25. And this is 0.25. Look at carefully. Mm, no dimension. Megapascal, megapascal. And देखो, mm, 4, D by T, megapascal. Okay. Now he is asking what is the radial displacement and what is the original radius, delta R by, what is the original radius? It is 1000. So this is 1000. So is equal to, let me calculate this value, 0.75. 0.75 into 1, 2, 3, 4, 5 by and into, so we are getting this as the total delta R value as 18.75 mm. Why in mm? Because this is in mm, so you are getting this as 18.75 mm. Let me cross check, sirs, whether it is right or not. Let me cross check. Yes, 18.75 is the right answer. No problem at all. Good question, sirs. No problem. Let's take the next one. This is a good question. Please read the question. A good question. Please read the question. Now, a cantilever beam of constant cross section is subjected to a positive bending moment. Okay, this is a positive bending moment. And an axial force, there is an axial force and there is a bending moment. The normal stress due to axial force is 200 megapascal. Due to F, I would like this, I will write this as direct stress due to F. And the direct stress is 200 megapascal. Okay. This is the direct. So due to this, I write it as direct stress. And the maximum compressive stress is the maximum compressive bending stress. And the maximum compressive stress is given as 100 megapascal. Good sense. And what is he asking? If the point A is located at the top surface, okay, don't worry, and B is located at the centroidal axis, The stress at these points are very good questions, sir. The direct is 200 and the compressive is 100. Chalo, let me read. Dear students, this is the cantilever beam. No problem at all. There is an axial force of F, and because of this, there is a direct stress of 200. I think it is 200. Let me check. It is 200. Yes, it is 200 megapascal. Very good. Now let me try to write the bending stresses. Okay, no problem at all. And you know, my dear students, if you observe clearly, the top fibers are in compression. If you see the deformed member, the top fibers are in compression and the bottom fibers are in tension. So the maximum compressive stress is occurring at the top. So let me show you this clearly. Let me show you this. So let me take the cross section. And dear students, if you take the cross section like this, okay, no problem at all. This is the neutral centroidal axis. Okay, no problem at all. And this is all tensile due to direct all the members everywhere it is. I am showing only because of this. Due to this, as it is passing through this, every member is subjected throughout the cross section. Every member is subjected to a direct stress of 200. So this I will write tensile. Is it tensile? Yes, it is tensile. So therefore, my dear students, it is completely 200. Everywhere it is 200. Everywhere it is 200. No problem. And clearly, the bending stresses are like this. You know, it varies linearly. Right. And you know, if you see the figure, the bending moment is like this. Therefore, the bottom fiber is in tension and the top fiber is in compression. So therefore, now I read, the bottom is in tension and the top is in compression. Right. So this is given as 100 if I am not wrong. This is given as 100. Yeah, the compressive is 100. So dear students, if the maximum compressive is 100, it is a rectangular section. Therefore, if the maximum compressive is 100, the maximum tensile is also 100. Great. Now he is asking, point A is at the top. A is at the top, this one, A. A is referring to this is A. And where is B? B is at the center. B is at the center, this is B. Let me check, sirs. B, yes, B is at the center. B is at the center and A is at the top. Now he is asking, if you just observe what is the stress at A, and you know, my dear students, the combined effect, 200 is tensile, and there is 200 is tensile, and there is a compressive stress of, bending stresses are in the cross section, so therefore it is 100. Therefore it is 100. So which one is more? Tensile is more. Tensile is more. So therefore, now at A, it is completely tensile of 100. At A, 200 minus 100. At A, it is tensile 100. And at B, if you see at B, there is only direct stress. There is no bending stress. There is at the neutral axis the bending stress is 0. At B it is 200. So therefore at B it is tensile. So therefore at B it is tensile of 200. It is tensile of 200. Let me check which one is correct. So yes, at B tensile 200. At A tensile 100. At A tensile 100. So the answer is A. The answer is A. Is it clear? Very good. Now without wasting time, let's move to the next one. This is a very simple question, sir. Dekho, a beam of flexural rigidity EI fixed at A and is supported by a linear spring of stiffness K, and K is given as EI by, K is given as EI by L cube. EI by L cube. No problem at all. Determine the compressive force developed in the spring. Okay. What is the compressive force developed in the spring? That is asked here. So don't worry. No problem at all. Aram se. Now, let's proceed, sirs. Let's proceed. Now, because of this UDL, there is a deflection at the end. And due to UDL at B, deflection at B due to UDL, I think you know very well, it is WL power 4 by 8 EI. Do you remember? I have derived all these things. So at this, there is a deflection. But when it is deflecting, the spring will compress and when the spring is compressed, it will try to come to its natural state. So the spring will start exerting force in the upward direction. Let F be the force, compressive force in the spring. Let F be the, so because of this load, it is deflecting, and as it is deflecting, the spring is compressed. So whenever the spring is moving from its natural state, the energy is stored, and thereby it tries to come back to its original position. So if F is the force in spring, it will try to come back, and thereby it will, this is in the downward direction. If the spring force is F, it will exert in upward direction. It is something like combination of UDL and point load at the free end. So therefore, look at, if the spring force is Fs, okay, so because of compression, this force is developed, and it will try to exert force like this, and thereby there will be deflection like this because of this. And when there is a point load at the free end, the deflection is given by FL cube by 3EI, and that is given by F in the spring L cube by 3EI. And there is a downward deflection, there is upward deflection. So net deflection is this minus this. So definitely, whatever there is a net deflection of this, the spring is also deflected by same. So the spring deflection is given by net deflection. So how much is the spring deflecting? How much is spring deflecting? This minus this, or this minus this, that is the net deflection of spring. There is downward, there is upward. Net deflection of spring is this minus this. So therefore, WL power 4 by 8 EI, okay, minus Fs L cube by 3 EI. This is the net deflection of spring. There is a downward load, there is an upward load. So there is a net deflection. So whatever this system is deflecting, the spring is also deflecting by same amount. So this is the net deflection of spring. Great. But you know, spring stiffness is given by spring force by deflection. Spring force by deflection. A deflection is given by Fs by K. So this delta can be written as Fs by K. So that is equal to WL power 4 by 8 EI minus Fs L cube by 3 EI. Wonderful. So let me go to the next slide. So that is Fs by K is the deflection of spring. WL power 4 by 8 EI minus Fs L cube by 3 EI. Fs L cube by 3 EI. So you take this to this side. So therefore, but already K is given. In the problem, K is given. What is K given? EI by L cube. This K is given by EI by L cube. That L cube will go to the top. EI by L cube is equal to WL power 4 by 8 EI minus Fs L cube by 3 EI. So therefore, take this to this side. So Fs L cube by 3 EI. Very good. Plus Fs L cube by 3 EI. No. There is no 3 here. 1 second. There is no 3 here. Okay. देखो एक बार Fs L cube by EI, you bring it to this side, is equal to WL power 4 by 8 EI. So take LCM 3 is common, 3 plus 1 4. 4 Fs L cube by 3 EI is equal to WL power 4 by 8 EI. So EI is gone. So L cube is gone. I think you are getting Fs as this 3 will come this side. So 3WL, because L power 4 L cube means L is left, 1L, 3 and 8 4. This 4 will come this side. 8 into 4 is 32. So the compressive force in the spring is 3WL by 32. Where is that? 3WL by 32. Wonderful, sir. This is correct. Wonderful. No problem at all. Go to the next question. I'll take a very good question. हाँ ये करेंगे सर. This is a good question. Take this. This is a good question, and this is an expected question. This is an expected question. Mark it as important. A cantilever beam AC is. I'm not saying you are going to get the same question. No. Concept may be same. A beam AC is composed of two segments AB and BC, and they are rigidly connected at B. The flexural rigidity of AB is EI, whereas the flexural rigidity of BC is infinite. What do we mean by flexural rigidity infinite? It means my Young's modulus is infinite, means it is rigid. Very good. Determine the magnitude of slope at B. He is asking slope at B. So whenever you come across such questions, there is a rigid member, there is a deformable member, this is a deformable member, and this is a rigid member. So whenever you come across such questions, I request you to go for strain energy method. No problem at all. So let's see how we proceed. Length. Dekho. There is a member. This is rigid. And this is deformable. This length is L. This length is L. And there is a load P. यार यहाँ पे place नहीं है ना. एक second please. There is a load P. And this is rigid. Okay. No problem. And he is asking slope at this point. This is A, this is B, and this is C. The total length is 2N. How do we do? एक काम करेंगे sir. Let us calculate the total strain energy. You know one of the Castigliano's theorems. What is that? If you want slope, you differentiate partially the total strain energy with the moment. Wherever you are, suno carefully. If you want slope at B, there has to be a concentrated moment at B, differentiate B. But unfortunately, there is no concentrated moment. And I have told you very clearly in my regular classes, if there is no concentrated moment, my dear students, you apply hypothetical concentrated moment. That is M. Finally, what to do? Calculate the total strain energy and differentiate partially with M. And finally equate M to 0 because there is no M. Wonderful, sirs. Now, this I have already told you, no problem at all. Ab dekho, you take any section X. From the free end. So here X is 0, here X is 0, and here X is 2L. Very good. And here X is L. X0 at C, XL at B, X2L at A. Now, what is the bending moment here? The strain energy is absorbed due to bending in this case. So therefore, the strain energy, the bending moment is given by P into X. Look at this length is L, so P into X. Very good. It is clockwise, and there is a concentrated moment also plus M. Wonderful, sirs. This is the bending moment at this section. P into X clockwise plus M. Okay, and I have taught you very clearly. The strain energy is given by M square L by 2 EI. In a complete, due to bending, the strain energy is M square L by 2 EI. So in a complete length L, if the bending moment is M, so I multiply this M square with throughout the length. But unfortunately, the bending moment is not constant. It is varying with X. So that's why what I do is, dear students, as the bending moment is varying with X. So this is, look at, ऐसा करेंगे सर, एक सेकंड. We have calculated here. So bending moment is varying with X. So that's why I take small x dx. Because bending moment is varying with X. If X variation is very small, in the small n, the bending moment is same. So I will calculate strain energy in the small n. If you want total, I will integrate. But now, m square dx लिखेंगे. But please, my dear students, understand carefully. Rigid members, they do not absorb any strain energy. Only deformable members absorb strain energy. So if this is completely deformable member, then I integrate from 0 to L because complete member is absorbing. But in this case, it is not a rigid, it is not a deformable member, complete member. So this is a rigid member. So this doesn't absorb any strain energy. So therefore, whatever the strain energy is absorbed, it is from this to this, therefore deformable member. So X should be, यहाँ से measure करें. So X should be integrated from L to 2L, but not this, not from 0 to L, not from 0 to 2L. 0 to 2L means complete it is coming, but this is not absorbing any strain energy because it is a rigid member. So it will not absorb. So be careful, my dear students. इस यहाँ से यहाँ integrate मत करना. You completely don't integrate. You integrate from this to this, this to this, this to this. So therefore, the total strain energy is given by इसको integrate करना. But only deformable members absorb strain energy. So integrate X from L, B to 2L, L to 2L. So you integrate from this to this, this to this, this to this, this to this. So this is not absorbing any strain energy. So therefore, now understand carefully. This is very important question, sir. That's why I consider this question to be very, very important. Now, देखो. So the total strain energy is given by integral L to 2L, not 0 to 2L. So 0 to L is not absorbing because it is rigid. Only this is absorbing. So therefore, m square. What is m square? Px plus m whole square by 2ei into dx. M square dx by 2a. Okay. So u is equal to 1 by 2ei. I am integrating directly. 1 by 2a. P square. What is x square dx? Directly I am writing, sir. चलो नहीं लिखेंगे सर आपके लिए. M square plus 2mpx dx. चलो कोई प्रॉब्लम नहीं. And the integration is from L to 2L. Let me explain. A square plus b square plus 2ab. Then take dx inside. Take dx. A square multiplied by dx. B square multiplied by dx. 2mpx dx. Okay. Now the total strain energy is 1 by 2ei and t square. What is x square dx? It is x cube by 3. What is this? M square. Integral dx is x plus 2mp. What is x dx? X square by 2. And limits are L to 2L. So therefore, so what I do is I'll erase this cell. यहाँ पे why to go for the other slide. Now directly I'll calculate here. So therefore, now the total strain energy is given by 1 by 2ei. हाँ. तो एक काम करो सर. And finally we are differentiating partially. A common sense use करना. ये पूरा substituting all, I think it is wastage of time. क्योंकि finally if you want slope you are integrating with m. And if m is left in the final equation, we'll put it as 0. तो यहाँ पे कोई m नहीं है. There is no m here. तो automatically partial derivative क्या होगा? There is no m here. So partially you are differentiating with m. There is no m here. वैसे भी ये मर जाएगा. So इसको differentiate करो. 2m आएगा. But finally m is left. Finally 2m. m आएगा. तो finally m should become 0. तो ये भी जाएगा. सिर्फ ये बचेगा. So therefore you have not understood. Let me tell. Otherwise you do routine manner. There is no problem. पूरा limit substitute करो. You substitute limits and differentiate with m and then equate m to 0. And there is no m here. Partial derivative of this will be automatically 0. Now if you differentiate this, m square means 2m. 2m means m is there. Finally you have to put m0. तो ये भी जाएगा. So only this is left. So you differentiate this. So do you? If you differentiate this, it will be, देखो, p बचेगा. There is 2ei. 1 by 2ei. 1 by 2ei. So differentiation of m is 1. P x square. Limits देखो. X square means upper limit is 2l whole square minus lower limit is l square. So this will be equal to 4 square minus l square is 3. So 3pl square by 2ei is the slope. 3p square by 3pl square by 2ei. 3pl square by 2ei is. Otherwise, if you have not understood, I'll tell you. पूरा limit substitute करो. After substituting limits, you differentiate with m. So anywhere there is no m, ये तो 0 हो जाएगा. Differentiate with m, 2m. So 2m, finally you have to put m0 because m is not there. You have imaginary, this is imaginary m. So finally it should be 0. So when you differentiate with m, ये सिर्फ this is left. Therefore I have taken limits here. Otherwise you can do it. So there is no problem. Thank you, my dear students. So hope you have enjoyed. I'll come up with many more such classes. Thank you. God bless you. Thank you.